So last time we did a quick little thing on magnetic forces on charges and sort of showed how to use right-hand rule number 2, which I know can get kind of confusing. You get the circular motion involved, that kind of stuff. It just gets annoying. Kind of hard to visualize. So we're going to use this a little bit today in this video, and so I can show you a little bit of how this actually looks like. So hopefully this will help a little bit. So this is like an XYZ coordinate system. There's this dark thing right in the middle. That's actually that's a point charge. Actually, if I slide, I can move it around. So that's actually a little charge right there. And I can change its position. I can put it wherever I want. It doesn't make a difference. I'm going to put it right. I'm just going to put it right there for now. That's fine. Okay. Now, if I give it some velocity or something like that, it can move around and do different things. So as long as if I can see and get a little velocity in the X direction here, there's a little, you see a little velocity vector popping up, and I can click go, and then off it goes. Okay. No big deal. So whatever. So let's see if we can sort of show you what the magnetic field thing is. Now, so I want to give it a little velocity vector. I want to have it going in the X direction along that coordinate system right there. And I am going to, yeah, we'll just leave it there. I'm going to introduce a magnetic field, and I'm going to have the magnetic field going down. So if the magnetic field is going down, so I'm going to give it a magnetic field in the negative Z direction. So the magnetic field's actually going down opposite of the green vector, and that blue one right there is the force vector. So if you take your right-hand rule and you point your shooting finger in the direction of the red one, your thumb should be in the direction of the blue one, because that's the force vector, and your fingers, your three remaining fingers, should be pointing down. And if I let this thing go, it will go in a circular path, just like that. Okay, so this is how magnetic fields create circular motion for subatomic particles. And I can even change the magnetic field a little bit. And so instead of the magnetic field going in the Z direction, I'm going to have the magnetic field going in the Y direction. So I'm going to have a magnetic field going the Y direction. So for this one here, your gun will be pointing, again, we haven't changed the red one, that's the velocity vector for this sim, and your gun's pointing in the direction of the red one. The blue is the force vector. I would use the blue for the magnetic field, but whatever. The simulation has the blue for the force. So your fingers pointing in the direction, your shooting fingers pointing in the direction of the red one. Your thumb is pointing straight up for the force, because I made the magnetic field going sort of to the left in the Y direction. So if I let the charge go, it will go in a vertical circle going around and around. We can even change this around a little bit again here. Let's just even change the velocity vector. So instead of it wanting to go in that direction there, and let's take the B, make it 0. Let's just sort of reset everything. So suppose we have the velocity going in the Y direction. So I'm going to have it going out that way. So that's the way your finger should point, your shooting finger to point in the direction of the red vector right there. And I'm going to make the magnetic field going in the negative X direction, which causes the force to be up. So your gun fingers, so to speak, for your right-hand rule number 2, pointing the direction of the red arrow. Your thumb is the force vector, so that is pointing straight up. And it means the magnetic field is going sort of like down leftish, the negative X direction, which is what I've set it at. And I'll let the particle go. Come on, go. There we go. There it goes in a circle just like that. Okay, so hopefully this helps visualize how these particles actually move in fields and different things like that. Now, again, pretty much everything you guys have done, we've always had in the QVB expression, sine theta is being equal to 1 every single time. And I can sort of show you why we want to have, for you guys, everything perpendicular. Because if it's not perpendicular, things get really kind of complicated. So let's see if we can introduce a couple more magnetic fields. So we are going to introduce another magnetic field. So this is what would happen if it wasn't at an angle. You sort of get spiral shapes often happening. And this is one of the reasons that we don't want to incorporate too many angles with you guys, because you get spirals occurring. And if I can click and drag it, if I can click and drag it, you can sort of see like there's a circle in one dimension. And if I could go vertically, it won't let me turn all the way around, it would be a circle in the other dimension as well. So we get spirals out of it, and that's the annoying thing. Actually, I can turn it this way, you can see a little better. So if you looked sort of from the top, is sort of, you have a wave function is what you actually have. Okay, so there's a nice wave function right there. And then from the end point, there's your perfect circle right there. So this is what magnetic fields and angles can do with charges. They can have them do like corkscrew shapes and spiral shapes to get them moved like this. So this is why you guys just do 9 degrees each time to keep it nice and simple, to keep things just focusing on just basic circles. That's all we want to worry about. Actually doing this stuff isn't necessarily hard, but we're just worried about the basic circles. It's all about the basic ideas. You guys can worry about stuff like this in university or college or whatever else it might come up in a few years, but whatever. Okay, so I'm hoping this helps you guys to visualize the circular motion thing that we're talking about before. It also helps practicing on the right-hand rule a little bit. If we could have, I can't change this to a negative charge. If we could, then we could practice using the left-hand rule as well. But remember, for negatives, just use the right-hand rule and flip it. That's often the easiest way to do it. But hopefully this video will help a little bit with that right-hand rule number 2.